Thank you, Pranav, and thank you for coming here. Afternoon Tuesday is always difficult, but I appreciate your being here. So today I'm going to present you a framework that we have been working on for a long time. This is a working framework. I'm not going to show you a lot of simulations in this talk. I'm going to focus more on the framework. Tomorrow there's a session on how we use this in a real case, for example. So if you have time tomorrow morning, 11 to 1, I think, there's a session that you can attend to actually see how we apply this. But I want to acknowledge my collaborator, Jason Weiss, here. So where we come from, why we need this, why we do this is, there are many reasons, obviously. Reactive transport modeling is useful for many things. But there's a drive to reduce the carbon footprint of concrete, and that includes reducing the cement content, reducing the clinker content of cement, and making your structures last longer. Now, to do this, we have been very creative in two fronts. One is optimizing these mixtures in a way that they perform better, right? The other thing is that we also have to understand how these systems behave under various exposure conditions. Now, this is not as easy as before. If 20 years ago, when I was doing my PhD, we had OPC, we had SCMs, very well-defined systems. We were able to characterize these systems well and do service life modeling very easily, or I wouldn't say easily, but at least in a straightforward way. Now we are dealing with materials that are very interesting. We are being very creative in using different types of materials. Alternative SCMs, off-spec SCMs are more and more used. PLC with high limestone contents, etc. Very interesting waste products are being incorporated in concrete. And as the previous speaker said, the chemical composition of these materials are variable. There are a lot of variability in there, but also the reactivity of these materials show a very high degree of variability. Now, to document that, we have been at Oregon State University collecting data from different sources and also data generated by us on the composition and reactivity of various types of SCMs, and there's a DOI there you can go and find. We regularly update this document. When we get new information, we collect information about the variability. But what I want to say is that there's a huge variability. So if you think about fly ash is not a fly ash, it's not a fly ash. You have a large variability in chemical composition, and you have a large variability in reactivity. So how do you incorporate service life modeling on structures built with or constructed with materials, very innovative materials, low carbon footprint materials? How do you, for example, do service life prediction for corrosion or sulfate attack or freeze-thaw damage? That's basically the motivation of this work. In the core of all these service life models, you have to have several things that we do. Moisture movement, all those iteration mechanisms involve water. So water, monitoring where water is and which state your water is and which pores your water is in is very important. So these service life models need to have good moisture movement models. You also have to look at where the ions are going and how the ions are going. Ionic movement in these systems involve multiple mechanisms of transport, diffusion, electrical migration, chemical activity, and advection. And you also have to think about how, as these systems, water and ions, move into your cementitious system, your concrete, they will react with other things. For example, chlorides might be bound. If you have sulfate would basically react with certain phases. So you also have like carbonation, for example, is a big thing these days we talk about. So reactions have to be modeled. So I'm going to, focus on briefly about these ionic mechanisms. So let's say if you're interested in modeling ionic movements in concrete made with really interesting materials, you have to think about various transport mechanisms like diffusion, electrical migration, chemical activity, and advection. And again, this presentation is not intended to be highly mathematical, but I just want to show you that mathematically speaking, we can represent all of these mechanisms really well. There are good fundamental theory behind all of these mechanisms. Again, don't worry about the variables there. The whole point is that those mechanisms then can be merged into partial differential equations where you can use tools like finite element method or finite difference method to solve those transport problems that include very complex transport mechanisms. Now, this is one example of a partial differential equation to model ionic transport in concrete. Again, I intentionally blurred out some of those things here because my intention here is not to talk about this. My intention is to talk about the type of input that you have to provide into these models. For example, to solve that partial differential equation using finite element method or finite difference method, you have to know, you have to have experimental data on the system that you are modeling. For example, if you're modeling a concrete that's built with an off-spec fly ash with 15% limestone, and you put some very, very interesting stuff in it, and you have a water boundary ratio, etc., all those things, you need to know what the porosity is, and you need to know how porosity changes over time. You also have to know the diffusion coefficients of the ions that you're dealing with, because those are quantities that you have to have input into your solution. Again, these also change over time. On top of that, you have reactions. So that term, again, without understanding the differential equation, just take my word for it. That term there is basically the term that takes care of the chemical reaction. So you want to, for example, model how much of a chloride ion is bound by, for example, other compounds in your cementitious system to form like a Friedel salt or Kusal salt or calcium oxychloride. You have to have some empirical relationship to describe experimental relation, describe that mathematically. So what we used to do before was we used to obtain all these input data like porosity or empirical models for reactions or diffusion coefficients. This is activity coefficients, activity of the ions, etc. All these things were experimentally obtained. And there are a lot of experiments that you have to do, time-consuming, expensive experiments. And the problem with that is that those experiments can be error-prone, inaccurate, unrepresentative of the systems that you're actually intended to model. They can be very time-consuming. Some of this, like for example, to get a proper diffusion coefficient, you may actually have months of testing to get a proper data, and that's why expensive. So the idea that we developed was, can we obtain these input data that we need to solve these equations, like say using finite element method, using theoretical approaches instead of experimentally obtaining them? Can we get them theoretically? And that's what we call the self-sufficient reactive transport modeling. And when we say self-sufficient, it is not necessarily we don't need any experiments. I'll show you that there are some experiments we still have to do, but they're more fundamental than just doing a diffusion coefficient experiment, for example. So without going into detail how this overall system works, how we merge the transport problem with reaction problem is a completely different story, but it's a time marching algorithm, basically. You march your time at small time increments. At every time increment, while you're solving your differential equation, you're also calling an engine where the reactions are modeled. So that engine that models the reaction is what we call thermodynamic modeling. Thermodynamic calculations is used to replace actual experiments. In this talk, we're not going to go into how thermodynamic calculations work, but just understand that this is a very well-established area of expertise. A lot of researchers have dedicated their entire lives to develop these codes where they can model reactions, basically. So we couple transport code, like finite element codes, to solve those differential equations with thermodynamic codes to simulate reactions. And at every time step, we do a time march, solve the transport problem, ask to take care of the reactions. We do an equation balance, reaction balance to find what the equilibrium state is, and we move forward to another time step. So that's the idea of this. So how do we move from empirical to self-sufficient, from eliminating some of those experimental data and obtaining them theoretically? So the idea is that, as I said, we have these mixtures, very creative mixtures now, ordinary Portland cement, limestone, various types of SCMs with interesting sources, limestone and water. So we can say that using thermodynamic modeling framework, we can calculate what kind of products we form. We can, for example, calculate how much calcium silicate has CSH would form, how much calcium hydroxide will form, how much Friedel salt will form, how much calcium oxychloride will form. We can calculate the actual solid products that will form at different times. We can find those at 7 days, 28 days, 56 days, or any time we want. We also can determine how much or the composition of the pore solution. We can quantify how much ions we have in the pore solution, sodium, potassium, whatever. We can calculate electrical resistivity or conductivity of the pore solution. We can calculate the pH of the pore solution. And using that data, we can calculate things like compressive strength, porosity, electrical resistivity, formation factor, from that diffusion coefficients, time to critical saturation, pH, etc. So these parameters you would typically have to do experiments to obtain. We do these theoretically. The idea how this works is again described in multiple papers. So it's summarizing it. There are two experiments that are very important. One is that, for example, if you have ordinary Portland cement or Portland limestone cement or some SCM, first of all, you have to know the chemical composition. So self-sufficient does not mean that you can do everything without any experiments. You have to have the chemical composition quantified. So you have to use some like an X-ray fluorescence to get your chemical composition of your materials. The second thing that you need is that the previous talk mentioned is reactivity, especially pozzolanic reactivity of your SCMs. So you need some kind of a test to differentiate how much of your SCM is reactive, how much of it is not reactive. So I mentioned in my question that reactivity matches really nicely how much glass phase you have versus the crystalline phase. So you need a test to do that. So this pozzolanic reactivity test, the previous presenter mentioned an R3 test. There is another version of that we call this pozzolanic reactivity test. We just don't measure the heat release in the pozzolanic reaction. So we put some SCM react with calcium hydroxide in a water-present environment. And this is a pozzolanic environment. So you get some pozzolanic products that releases heat and of course consumes calcium hydroxide. So we plot the heat on the vertical axis and calcium hydroxide consumption on the horizontal axis. And every data point there you can see represents a SCM that we tested. We compare that point, for example here, the star here, or asterisk here, to theoretical values of pozzolanic behavior, and we get a quantity. Like, for example, that star is about 78% reactive. That triangle is about 59% reactive. That means that 59% of that SCM is going to take part in the reaction. So the pozzolanic reactivity test tells us how much of that SCM will react at a given time, like at 28 days or at 90 days. But that doesn't mean that, pozzolanic reactivity test means that how much of that SCM is possibly reactive at infinite time. You don't still know how much of that SCM that's available to react will react at 7 days, 28 days, 56 days, or 90 days. For that, you need kinetic models. So we spend a lot of time to get kinetic models to see how much of that available reactive SCM will react at different times. So those kinetic models are also described in several papers. And then we basically say that, let's say you want to know the reactions at 7 days. We say that, okay, at 7 days, you have this much of this OPC, this much of the SCM available to react. We provide those thermodynamic calculations, and those thermodynamic calculations give us things like properties that we need to use in several things. So does this work? And one of the works that, one of the biggest trusts that we do in this study is that we actually do a lot of validation. This is a validation data for porosity. So you can see that the experimental porosity and model predicted porosity falls into a really, really narrow band. This is for formation factor. Those of you who are not familiar with the formation factor is a quantity that can be linked to diffusion coefficients. So you can see that the experimental and model formation factors fall into a very narrow band as well. Now, you may also say, okay, how do you model reactions well? You might be familiar with chloride binding isotherms, for example, just to show that theoretical framework, the reactive transport framework that we use, can actually predict experimental chloride binding isotherms. I'm showing you some validation there as well. So the reaction part is also highly validated. So at the end, what I want to say is that you can solve these differential equations to do the service life modeling, and the input data that you need to solve these differential equations using finite element method or finite difference method need to be determined to do that. Either you can do those with experiments or you can do them with theoretical calculations, just I showed you. Even with the theoretical calculations, you need to do some experiments. Specifically, you have to quantify the composition of your materials and you have to quantify the reactivity of your materials. So the works like the previous researcher does definitely provides good insight into reactivity mechanisms, but we also need to have some bulk ways of doing that, and posonic reactivity test does that. So we did all the validation on reactive transport modeling, benchmarked with many other applications, and at the end of the day, I want to conclude that there is a path forward to incorporate these really interesting, innovative, and low carbon footprint materials into concrete and do service life modeling with them without getting into the path of doing extremely expensive and time-consuming experiments, at least to even narrow down the number of cases that you have to experiment. This kind of framework can be extremely useful. So we call this self-sufficient, but again, there is some experiments in them. So this work has been going on for a long time. A lot of people have been contributing to this. So there are some pictures here. I think Paranoid's picture should be here as well, but you can see him here. So Paranoid worked with us on some of these things for a number of years. We don't talk about him anymore because he's competing with us, but anyway, we're kidding, of course. But this is a good team that we used to have. We have new people, and we have a beautiful place in Corvallis. If you have time to visit us, we're happy to host you, and we're happy to show you what we have in our labs. Thank you.